All right. All right. Good morning, Lorenzo. How are y'all today? Doing all right? Good? All right. Um, let's see what's going on today. Oh, review. So today has been set aside to address your questions over the review. Um, we will have our exam on Wednesday and Friday this week, part one on Wednesday, part two on Friday. Um, and that's what we're doing this week. So, as additional things to look at, your quizzes have been graded, uh, posted on Gradescope, answer keys in Blackboard, so you can go through and look at those graded exams and compare them with the graded quizzes and compare them with the quiz key. I'll let you do that on your own. So my time today is to address your questions. How can I help you? So what can we look at in terms of the review?
Can we look at number 7, please?
Number 7. All right, before we get going, um, um, so I don't know if y'all remember, did y'all ever have Mr. Sean Fulkerson for math? All right, so he goes to my church, and he asked about what students I had, and I know I have Alejandro, but you go by Alex, right? You go by Alex. All right. I need to know the names of the ladies in the back. So let's start with the lady that's sitting next to the window, and we'll work to the other side of the room. So name next to the window. Yep, her. Yes.
Amaris.
Say it one more time.
Amaris.
Maurice? Maurice?
Amaris.
Maurice. Okay. And then
Ariel,
Ariel. So Maurice, Ariel.
Lucero,
Say it one more time.
Lucero,
Consuelo. Consuela. Consuela.
Lucero,
like Lucero.
Oh, Lucero.
Yeah.
Okay, there you go. There you go. The it's not always easy to hear through these microphones. All right. When I got small groups like that, I like to get to know the names. And another side note. Dang it. Well, Marcos. Do y'all know Marcos? Just graduated. I ran into him the other day. He was at the Reese campus, and he was taking a calculus class, and I ran into him. He's like, Mr. Clopton? And I was like, who are you? I couldn't tell because they had a beard now. And anyways, so, and he asked about y'all too. So, anyways, what can I do to help you? What questions do we have regarding the review? 7? 7 questions? Or problem number 7? Problem number 7. Okay. The piecewise function? Okay. Problem number 7. We have g of x is equal to x squared plus a 7x minus 1 if x is less than 4. And then we also have 2x minus 1 over a 3x squared minus 5 if x is greater than or equal to 4. And we want to find g at 2. Alright, so g at 2. So the thing that you got to look at is you got to look at the intervals that we have up here, the inequalities. And you're going to have to ask yourself, well, what inequality does 2 belong to? Is 2 less than 4 or is 2 greater than or equal to 4? Well, since 2 is less than 4, we're going to use, we'll call this equation 1 and we'll call this equation 2, use equation 1. That's the equation, and that's the only equation that we're going to use to find g at 2. So this becomes 2 squared plus 7 times 2 minus 1, which is 4 plus 14 minus 1. 4 plus 14 is 18 minus 1 is 17. So you're only going to use, even if this had 3 parts, even if there are 3 equations, 3 different intervals, you're only going to use one equation to find f or g at whatever function value. Now, oops, what happened? I'm going to take charge here for a little bit. Problem number 8 is dealing with the same piecewise function, and it asks for the domain. Asks for the domain of g of x. Same g of x that we have up here. Alright, so what you have to do is you have to think about this in 2 parts. So let's think about this on a number line. I think that will help. So do you notice that our 2 equations are divided at 4? So you use equation 1 for everything at less than 4, and you use equation 2 for everything that's greater than 4. So I'm just going to put 4 right here. Now, let's take a look up at equation number 1. Equation number 1 is x squared plus 7x minus 1. What's the domain of this equation? Well, this equation has no restrictions on it. There's no division happening. We don't have anything weird. In fact, if I just gave you this single equation, you would say that the domain is from negative infinity to positive infinity. Now, because we have to apply the domain of equation 1 by this inequality statement, we really are going to say that our domain is from negative infinity to positive 4. Because in equation 1, we're not allowed to plug in anything that's greater than 4 because this is only used if x is less than 4. So I'm going to come over here to my number line now. Let's circle the 4. I'm going to shade everything to the left. Now we got to do the same sort of thought for equation 2. Now equation 2, 2x minus 1 over x squared, 3x squared minus 5. Now if I said, let's just look at this one equation, this is equation 2, and I ask for this domain, well, there's a restriction on this domain because, remember, we can't divide by 0. So, to find out what x can't be, x cannot be whatever x makes your denominator 0. So, what makes our denominator 0? Well, we could add the 5 to both sides. Then I would divide by 3 on both sides. And then I would square root both sides. So, square root both sides. And you get x basically cannot be equal to plus or minus the square root of 5/3. Now, if I just take my calculator out real quickly, so I'm going to do the square root of 5/3. This is x cannot be equal to plus or minus, well, I'm going to just round to the nearest tenth, 1.3. Now, plus or minus 1.3, they're over here. 1.3 and a negative 1.3. But you have to be thinking about this. When you're looking at equation 2, the only time that you use equation 2 is when x is greater than or equal to 4. So I wouldn't be using 1.3 or negative 1.3 if I was told to evaluate. If I said to find g at 1.3, you would actually use equation 1. Because 1.3 is less than 4, you would actually use equation 1. And we don't have a problem plugging in 1.3 into this equation. We're going to get some value out. So even though 1.3 and negative 1.3 are restrictions on this equation, we wouldn't use 1.3 or negative 1.3 for this equation because we only use this equation when x is greater than or equal to 4. So, since this is going to supersede, it's basically just going to cancel this thought out. We can say our domain here is all things that are greater than or equal to 4. So I put a solid circle around the 4, and now I can see that by this graph that my domain of g of x is everything from negative infinity to positive infinity. I can plug in anything I want into this piecewise function. Again, the only restrictions that I have on either two of these equations is for equation 2 when x is plus or minus 1.3. But since those are less than 4, I would only plug those into equation 1. Okay. Back to your questions. What can we look at?
Can we go over number 17, please?
17. Okay, 17. So we are told to answer the following questions about a graph. I'm going to roughly draw this graph. So we got -1, -2, -3, and -1. And the only bit of stuff that we have in this graph is it looks like we could say that the vertex is right there. That's basically all that we have from this graph. Alright, so I think that's a pretty fair representation of what we see on 17. So, problem number A, on what interval is the function increasing? Alright, so I want you to ignore the y-axis. I want you to cover up the y-axis if you can, because for this question, we don't need the y-axis to tell us when the function is increasing. In fact, I can look right here, anyways. Let me just erase that one for right now. Gone. Alright. I don't have to look at the y-axis to tell me when the function is increasing. I'm just going to think about writing the graph. So as I'm writing the graph from left to right, I'm going down, and then all of a sudden, I start going up. So the question is, when did I transition from going down to up? Well, I transitioned at this x value of -2. That transition point was at x equal to -2. So we are increasing from -2 all the way up to infinity. And I'm not talking about infinity along the y-axis. I'm talking about infinity along the x-axis. I'm talking about infinity on the x-axis. So as I move from -2 onwards this way, my graph is always going to be shooting up. As I move from -2 this way, my graph is always going in the upwards direction. And then the next question is, when is the function decreasing? Again, I don't need the graph to see where the function is, or I don't need the y-axis to see when the function is decreasing. As I look at this from left to right, we can see that it's decreasing all the way until we get to x equals -2. So, way back here at negative infinity, the graph, you can just imagine it. The graph is way up here, it's going down. So as I move along the x-axis, my graph is going down, 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 all the way until I get to the point -2. So we're decreasing from negative infinity to -2. C. That really should say, is there a maxima? Maybe, I don't know, maybe it should be maximum. But there is no max. There is no maximum point. Number one, there's no transition from increasing to decreasing. We don't have that. And we can't say that infinity is the maximum point, because what is infinity? As soon as you say that infinity is the maximum point, well, all I have to do is add 1, and I beat you. I said, no, infinity isn't the maximum point, infinity plus 1 is. And then you start playing that a game for all eternity. So there is no maximum, but there is a minimum. A minimum occurs at this transition point from decreasing to increasing. And a minimum occurs at, and we're just going to give it a vertex. That vertex is at, I'm going to throw my y value back in there at, and this is really we just have to do our best look at this and say it's at -2, -1. I would say if you said -2, -0.8 because you weren't quite convinced that it was that -1, I would still call this okay. because when you look at the graph, it's really hard to tell, is that really at -1? But I would just round up to the nearest integer. Does that answer your question? About 17? Okay. What else can we look at?
Three C.
32?
Three C.
Oh, 3C. Really missed that one. Three C is y a function of x? So this is a good question, and so let me give you some easy ways to distinguish if y is a function of x. If y is equal to plus or minus x, then it is not a function. If you get the situation where y is equal to plus or minus x, then it's not a function. So if you look at C, where we have x minus 5 quantity squared is plus y plus 8 quantity squared is equal to 16. If you take this equation and you start working to solve for y, look what happens. Y plus 8 quantity squared is equal to, let's do 16 minus the x plus 5, or x minus 5 quantity squared. And then, if I want to get y by itself, I got to get rid of that exponent of 2. So you have to end up square rooting both sides, and what happens when you square root both sides? You have to include the plus or minus notation. So you end up with a y plus 8 is equal to plus or minus the square root of 16 minus x minus 5 quantity squared. And already, since I have the plus or minus right there, already I can just say y is not a function of x. Because when I started the solving process to get y by itself, I ended up with a plus or minus. Now, why the plus or minus? Let's ask this question. Why did we get the plus or minus? Well, the reason that we had the plus or minus is because we had this y minus 8 to the exponent of 2. I'm going to highlight that exponent of 2. That exponent of 2 is what caused us to take the square root of both sides, and then also what caused us to get the plus or minus notation. That's why this is not a function of x. That's why this is not a function of x. Also, we didn't, here's my also statement. Also. Now, when we approached this section, we didn't know what this equation was. But we now know that this is an equation of a circle. Don't we? We know that this is the equation of a circle because it fits that format of the equation of a circle. And we know that circles are not functions because they do not pass the vertical line test. So again, we didn't talk about this equation when we approached this section in our unit. We hadn't talked about what this equation looks like, but now that we know what this equation looks like, we know, oh, that's a graph of a circle, and we know that circles are not functions. Wow, so does that make sense? Okay. What else can we look at?
Eighteen.
Did you say 15?
18.
18. Alright, so before we talk about 18, looking at the questions, let's do a refresher. Even functions. Even functions are always going to be of the form. Let's look at their graph first. Something like this. Or something like this. Oops, missed the mark. They are what we call symmetrical about the y-axis. So you could do a mirror image on the y-axis, and the left-hand side would be equal to the right-hand side. So that's their graph. They also, when we talk about their equations, they are always of the form f of x equals x to the n plus a, where n is even and a is constant. So as long as n is even and a can be any constant value you want, so you could even have a function, so I know I drew these that touch the y-axis, you could have one that does this. Or you could have a function that does stuff like this. I'm going to do my best to draw this. Something like that. They're all symmetrical about the y-axis. They don't necessarily have to touch the x-axis, but they have to be mirror images on either side of the y-axis. So that's even functions. Let's do a reminder about odd functions. All odd functions are going to be the format, or let's talk about their graph. They're going to look something like this. Where these are symmetrical about the origin. They are symmetrical about the origin. So, what do I mean symmetrical about the origin? You have to think about reflecting twice. So let's take this side of the equation. If I reflected about the y-axis, you get, I meant to do gray. You get something that looks like that. And then if you reflected it about the x-axis, there you get this graph. That's symmetrical about the origin. What else could we have? We could have a graph that does something like this. That would be symmetrical about the origin. Or you could have a graph that does this behavior. All of those are symmetrical about the origin. A counter example, this is not, so take any one of these functions and just move them up or down. That is not symmetrical about the origin. That is not symmetrical about the origin, because if you do your reflections, you're reflecting that way. Then if you reflect across the x-axis, then you're reflecting down this way. And that's not what we have over here. So that's not symmetrical. So going back up here to our definitions, the equation will have the form f of x is equal to, you could do ax to the n. You could have a factor in front of the x where n is odd. So there's our reminder about even and odd functions. So number A, we have this 8x to the 10th. Now, if that's all I had, this would be an even function. But as soon as I put the minus 4x to the 5th plus all this other stuff, I mean, if this is all I was looking at, I could say that would be even. If this was all I was looking at, I could say that it could be odd. But since I'm mixing things together, this is neither even or odd. It's a mix. It's a mess. You have all this stuff that's happening on over here. It's not going to be symmetrical about the origin. It's not going to be symmetrical about the y-axis. B, we have that y is equal to 2 to the x. So that's equivalent to 2 to the x to the first. Since 1 is odd, that 1 is odd, we know that this is an odd function. Now, you've also talked about graphing in this unit. So look at the graph of this guy. This graph says that my slope is 2, my y-intercept is 0. So I'm going to start at 0, and my slope is 2, so I'm going to go up 2 over 1, up 2 over 1. I could go in the reverse order, down 2 over 1, down 2 over 1, and yet you have just a line. But is this line symmetrical about the origin? Sure. Reflect this, so you're going to go up 2 over 1, up 2 over 1. So there's your reflection about the y-axis, and then you reflect this about the x-axis, you're going to get that line right down there. So this is an odd function. And part C, we have a graph that looks something like this. I didn't do a great job about representing that graph, but can you see that we have mirror reflection? If we reflect this side over here, we get a mirror reflection. So since this is symmetric about the y-axis, this would be even. Alright, so does that help with problem number 18? Alright, cool. What else can we look at?
Number 2.
Number 2. So we have the graph that looks something like this. Now, the one thing I don't like about this graph is what's happening on the right hand side. And I'm just going to go ahead and declare that since there's no open or closed circle, let's just go ahead and put an arrow. Let's put an arrow. Yeah, I'm not sure why that graph doesn't have that arrow telling us to keep going. But anyways, let's answer some questions. And we can change up these, well, we can, anyways, let's just answer these questions. Domain. So remember, domain is a set of x values that you have on this graph, that are represented on this graph. So the x values start here at -2, and they go on, because the arrow tells us that they continue on, we can declare that our domain is from -2 to infinity. B, we want to know what is the range. Well, range is a set of y values. So this graph, when you think about the y value, starts right here, and it will continue to go up. This graph will, at a very, very slow rate, the rate at which it increases will continue to decrease, but it will go up indefinitely. So we would say that the range here is from 1 to infinity. And the next question, is this a function? And I would say yes. And notice it says explain your answer. So that's part of your work. Explain your answer, and I could just say because it passes the vertical line test. It is a function because it passes the vertical line test. Does that make sense? Now, I want to play around with this just for a second, okay? Your test will not have any questionable values, but so it looked like if you were to say, where does that graph stop in the original problem? It looks like it would stop right there. So I'm going to put an open circle right there. So that's going to change some aspects of this graph. Instead here, now our domain is going to be from -2 to 1. Because this is as far as the graph is going. And our range would be from 1 to 3. And that would be the only difference. If we put an open circle right there, excuse me, sorry, I messed up. We would not have parentheses around those values. What would we have around these values instead, or brackets? We would have parentheses. Why would we have parentheses? Because we're not actually getting to x equal to 1, we're just getting really close to it. We're not actually getting to y equals to 3, we're getting really close to it. But it's still a function. For every single x that's in the domain, you draw a vertical line. That vertical line only interacts with the graph once. Does that make sense? Alright, what else can we look at?
$27.
Did you say 7 or 27?
27.
27. So we're given that f of x is equal to x to the third minus 7x squared plus 5x minus 6. And we're told to find f at 3. But we're not told just to find f at 3. We're told to find f at 3 using synthetic division. So the idea here is that the remainder theorem will say that f at 3 is going to be equal to the remainder f at 3 is the remainder of f of x divided by x minus 3. That's what the remainder theorem says. That the function f at 3, or the function f of x, if you evaluate it at f of 3, is going to be the remainder when you take f of x and divide it by 3. So remember, we're dividing by x minus a, so this means that our a is going to be equal to 3. So let's set this up. Here's 3. Here's our upside down division box. Coefficients of 1, -7, 5, -6. Let's go through and do synthetic division. Bring down the 1. Then we multiply. 1 times 3 is 3. Then we add. -7 plus 3 is a -4. And we're on repeat mode now. -4 times 3 is a -12. Add. It gives us a -7. Multiply by 3, that gets us a -21. Add. and we get a negative 27. So remember, the coefficients that we have up here represent x to the third, x squared, x, and our constant. We drop a degree, x squared, x, constant. This is our remainder. So this means that since negative 27 is our remainder, this means that f at 3 is equal to a negative 27. And there's our answer. Now, if I give you this question or a question like it on the exam, part of your work is to use synthetic division to find f at 3. That's how you get, that's probably going to be the main credit. If I said that this problem was worth 3 points and you didn't use synthetic division to find f at 3, I'd probably knock off 2. If you just plugged in 3 into this function and tell me negative 27, I'd probably give you 1 out of 3 points because you didn't follow the directions. Gotta follow the directions. Got to evaluate this using the remainder theorem. Now, certainly it's fine to check. By all means, check this out. Make sure that you did this correctly. So to check this, we're going to just plug in 3. So we're going to have 3 to the third minus 7 times 3 squared plus 5 times 3 minus 6. So it's going to be 27 minus 7 times 9 plus 15 minus 6. So it's going to be 27 minus 63. Go ahead and do that. 15 minus 6 is going to be 9. And then the 27 and the 9 make a 36. 36 minus 63 is a negative 27. So that checks out with what we got up there. So there's my check work. But again, to receive full credit, you have to not only get the 27, but you have to get the 27 using synthetic division. Does that make sense? Good. Alright, we got about 4 minutes left, maybe time for one more question. What do we got?
$26, please.
26. Did I hear that right? Alright, looks like we're doing a synthetic division. Five x to the third minus a 6x squared plus 3x plus 11, and we want to divide by an x minus 2. So remember that you're always dividing by x minus a. So this means that your a is equal to 2. So there's our 2 that we put right out in front. 5, negative 6, 3, 11. Let's play the game. bring down to 5. 5 times 2 is 10.
Your conference is scheduled to end in 2 minutes.
Thank you. Negative 6 plus 10 is a positive 4. Multiply. It's 8. Add, you get 11. Multiply, you get 22. Add, you get 33. Hopefully I did all my math right. Did we do that right? Is that what y'all got? Yeah? So, remember, x to the third, so this is x squared. So we have 5x squared plus 4x plus 11 plus, you write your remainder as 33 over what you divided by. That was divided by x minus 2. There's our final answer. Okay, well, we have less than 2 minutes left. If you have any other questions, I'm available by email. You can just shoot me an email. Hey, can we go over problem number whatever? And I will reply to your email. So shoot me an email today or tomorrow. If you shoot me an email, after 5 o'clock tomorrow, I may not get around to responding to it. My evenings are busy with making dinner and getting kids ready for bed and all that stuff. So if you're thinking that you have any more questions, make sure to get them to
Your
me
conference is now over. Goodbye.
as soon as possible. I'll see y'all later. Take care. Bye.